Hi everyone, let's start now. We're already 81 of us here, and I'd like to welcome each and every one of you to the webinar, Optimizing Statistical Power, where we'll be discussing essential strategies for sample size determination in health and social science research. So on this very auspicious Friday, I'd like to thank Felix for hosting this webinar and for agreeing to facilitate for our larger authored community. This is jointly organized in collaboration with the Authored Data Science Hub. Moving ahead, so there are a few ground rules that I'd like to share with you before introducing Felix. We are recording the session and your participation will indicate consent for the recording. The message must have popped up on your screen already. So the closed captions are available. So if you click the more option that you can see, if you hover your mouse, you can see the caption there. If it is not right there, you can access it via clicking the three dots, the more. If you have any technical issues, please let us know via chat or email me at asta.subedi@inapps.info. And to reduce the background noise, we'd like to request everybody to mute themselves except when you are speaking or asking question. Please raise your hand in the participants panel if you'd like to ask the question during Q&A, and the question and comments can also be submitted anytime in the chat, but we have separately allocated the question and answer session for the half an hour after the lecture portion. So please make full utilization of that. This is not one-sided method of teaching and learning, and I hope that you understand it and participate to the fullest, and you have a very happy learning Friday. So I'd like to introduce Felix and hand it over to him. He's an accomplished researcher, analytics and data science professional with driven solution, with demonstrated ability to develop and implement data-driven solutions in the urban and health sector, with over 10 years of experience in teaching and leading epidemiological, biostatistical, and data science projects from descriptive to predictive analysis. He is also a trained research scientist, scientific writer, and epidemiologist in his day-to-day duties at the Center for Health and Development, a center that evolved from several years of international research collaborations between the University of Port Harcourt and Lana University of Public Health at the University of Toronto, Canada, and most recently the University of Ottawa, Canada. CSD aims to develop human and organizational capacity for health-related research and quality healthcare provision in the Niger Delta region of Nigeria, built on sustainable local structure and international collaborations. He is a convener of Authored Data Science Hub, one of the guest facilitators for Authored online courses, and a biostatistician for the Authored online journal club project in apps. Also, he advises on a potential curriculum for statistical data analysis online course. And now I'd like to hand it over to him for the rest of the evening. I'm here for any technical support that you might require during your time here. Please enjoy the session. Over to you, Felix.
All right, thank you, Asta. That's a very lovely introduction. Thank you so much. So welcome, everyone. This is going to be a very interesting and exciting session. I hope you can all hear me. So I'm going to be sharing my screen right away. So today we'll be looking at optimizing statistical power, essential strategies for sample size determination. So I would try as much as possible to bring this information in its simplest form, because this is a topic that a lot of times, you know, I have to mentor students so many times for them to grasp it. Yeah, which is why we are taking a little more time, you know, so that I would have to take it a bit slowly. But during the Q&A, you have the opportunity to actually ask questions if there are areas that you are still not clear. So in order for us to appreciate the statistical power and how it relates to sample size determination, I would take it from the foundation. So I intend not to go straight to the statistical power so that you can appreciate why we are using statistical power and why the whole essence of sample size determination. So the sections are in three key places. We would look at study design, hypothesis test, and test of significance. Then we would look at the power and sample size calculation because they have some kind of link. So going straight to the power and sample size calculation, some may be lost, on the purpose why we need that. So I would take it, like I mentioned earlier, from the research angle, then you would see how the power and sample size calculation fits in. So the first thing I would talk about is research, which we'll all do. Now, a very good definition is the systematic investigation into the study of materials and sources in order to establish facts and reach new conclusions. In other words, research is simply a pattern. Like I mentioned, a systematic investigation, something that follows a process, something you don't just decide how you want to do it. There are laid down principles, there are laid down practice, there are laid down patterns on how these things should be done. So if you have made up your mind that you want to do research, then you have to follow that pattern. You can't decide, oh, this is what I want to do. No, it's not allowed. It's just like in the military or in the police force. If they're investigating a case, they have a standard operating procedure on how a case is investigated, and that could cut across the different cities, the different metropolis, the different districts. So they would have that standard operating procedure so that if you say you want to carry out an investigation, this is what you will do first, this is what you do second, this is what you do third. You don't just decide to do what you want to do. That's how research is. If you say you want to do a research, they have a laid down principles on how you have to go about it. You don't just decide how you want to do it. No. That is why whatever research that is done, the goal is for that research to be reproducible. So that someone, if you had done that research in Ghana, if you had done it in Tanzania, or you have even done it in the UK, somebody somewhere in Botswana or Namibia can actually look at that study and reproduce it in their setting. And the only reason why that could happen, the only reason why there could be a possibility of that happening is because the methodology, the process, the systematic pattern investigation that you follow is understood. So anyone can actually reproduce and replicate that study. So that's what research is all about. And one of the things that fall into this pattern is sampling method. You don't decide how you want to choose the people that will fall into your research. You have to follow a probability sampling method, meaning a method that gives every participant you want to be part of that study, you want to give them an equal chance of being selected. So you follow a sampling method. And that sampling method, sometimes it could be random sampling, where you have a sampling frame of all the list of the participants that you want to interview, and you randomly pick the number you need. And the number you need is based on the sample size calculation you have done. And you have to ensure that the sample size you are using for that study has to have enough power. You see how they link? So for you to be able to pick the number you need, you would have calculated a sample size. But you don't just pick that number, you follow a systematic process. Either it's random, either it's stratified, either it's cluster. Now, every study you do, you have to appreciate the fact that that study has an exposure and that study has an outcome, especially in the health and social sciences. There's always an exposure, there's always an outcome. Like in the example that I gave here, the first exposure is elevated temperature. And you can see the outcome right there. You can see the outcome right there, heat-related death and illness. The second exposure worsened air quality. And you can see the outcome, premature death, acute and chronic cardiovascular and respiratory illness. So in most cases, the study you do would have what the participants are exposed to and the outcome. Like in the study, one of the studies that I did, where I looked at an exposure, which is exposure to loud sound, excessively sound pressure level. And what was the outcome? Noise-induced hearing loss. So you would have an exposure, you would have an outcome. And having the exposure and having the outcome will motivate you to see what are the explanatory variables, independent variables that are influencing the outcome. So in the case that I gave, which is exposure to excessive sound pressure level, which is the outcome, which is the noise-induced hearing loss, you may want to find out what are the other factors apart from the excessive exposure to loud sound pressure level. That is one. What are other factors you would like to investigate that may make the participants susceptible to having noise-induced hearing loss? That is where hypothesis testing comes in. Hypothesis testing comes in when you want to see how the independent or the explanatory variable influences the dependent or the outcome. You will not have a hypothesis testing if you are not checking association or relationship of two variables. Hypothesis testing only happens when you are looking at how one variable influences another variable, how the age influences noise-induced hearing loss, how exposure to soot will influence respiratory tract infection. That's when we have a hypothesis testing, because you're looking at how one variable, which will be the explanatory or independent variable, would influence the dependent or outcome. And the hypothesis testing could either be a null hypothesis or an alternate hypothesis. The null is usually the state where there's no association before you carry out the research. So if we use the example that I gave, which is age and noise-induced hearing loss, our null hypothesis could be there is no association, there's no significant difference between age of the participant or respondent and they are being susceptible to noise-induced hearing loss. That would be your null hypothesis. And the null hypothesis is usually stated before you even do the research. So the moment you have a hypothesis, association of two variables, you state a null hypothesis. So you only have one outcome in every research. You only have one outcome. So in this example I'm giving, the outcome is noise-induced hearing loss, but you can have several exposure variables. You can have several exposure variables. You can have age, you can have educational factor, you can have how long they listen to loud sound, and the rest of them. So you can associate all these independent or explanatory variables with the outcome. That's your no association. You now carry out the research. Now, if there's no significant difference, you accept your null hypothesis. If the association you've done did not show any significant difference between the two variables you are associating, then you accept the null hypothesis. But if there is a significant difference in terms of the p-value or whatever the test of significance would be that I will show you later on, then you would reject the null hypothesis and accept your alternate hypothesis. So, which is this I have already mentioned. However, whether you would reject or accept your null hypothesis is usually based on a reference value or a reference alpha value or a reference probability value or a reference p-value. So that reference p-value is actually less than or equal to 0.05. So if you had done that association and your p-value is less than or equal to 0.05, then you're going to reject the null hypothesis and accept your alternate hypothesis. Now, this example we have here, a statistician responds to a marriage proposal, and he said to the lady, "Will you marry me?" And the lady says, "I reject the null hypothesis." And the guy went on wondering, what does that mean? Now, in this scenario, guys, here you would agree with me that the null hypothesis for a proposal is no. Every guy that proposes to a lady, the default is that the lady will not agree. That's the default. So you are proposing to the lady and you're very scared, like wondering, will she say yes? So what does that mean? It tells you that the baseline is no until she says yes. So will you marry me? And the lady says, I reject the null hypothesis, meaning I reject no. So I reject the null hypothesis simply means I say yes. You know, so the null hypothesis is usually the baseline, that line before you do that research. And if you're going to accept or reject your null hypothesis. So I think before I do this, let me take this first. The null hypothesis, the hypothesis is tested by several things, okay, depending on the type of variables you have. That's what you're going to use to test the null hypothesis. So if you're going to be checking for differences in two means, the test of significance you're going to be using for checking differences in two means would be the student t-test. If it's a pre and a post mean, then you're going to be using the paired student t-test. If you're going to be looking for differences in 3 or more means, then you're going to be using the analysis of variance. And that's for the parametric, where you have chances of a normal distribution of your data, meaning that in your data, you follow the systematic process in selecting your sample. So that way you probably not be having skewed data. So parametric, method of data analysis will be appropriate. So you will be using the t-test or the ANOVA. But in a case where you did convenient sampling, no form of systematic process in selecting your sample, there's a good chance that your data may be skewed. So you would be using non-parametric. So in non-parametric, you would be comparing medians instead of means. So why in the parametric, checking differences in two means is the student t-test. In the non-parametric, checking differences in two medians is the Mann-Whitney. Why in the parametric, checking differences in 3 or more means, you use the analysis of variance as the test of significance. But for the non-parametric, 3 or more medians, you use the Kruskal-Wallis. And you have to appreciate the fact that every test of association or every test of significance you do will generate a p-value. So it is that p-value that will give you a clue whether you're going to accept or reject your null hypothesis. So when you're checking for differences in percentages, then you're going to be using the chi-square. But in a case where the association of percentages you're doing, one of the values in there is less than 5. Maybe you have frequencies that are like 2, 3, 4 inside the association that you're checking. Then the Fisher's exact is recommended, not the chi-square now. Chi-square is usually numbers that are 5 and greater. But when you have numbers that are less than 5, the Fisher's exact is the appropriate test. It's a type of a p-value. All right. If you're using a Fisher's exact, you don't need a chi-square. I've seen an instance where someone would put a chi-square and now put a Fisher's exact. That's not correct. A Fisher's exact is a type of a p-value and it doesn't require a chi-square. But if you use a chi-square, then you would have a p-value alongside it because it's the p-value that gives you a clue whether you're going to accept or reject your null hypothesis. So if you're comparing two continuous variables, if one is increasing, is the other decreasing, then the Pearson's correlational coefficient is appropriate. But when it is ordinal variable, like, Likert scale, where you have agree, disagree, strongly, those kind of Likert scale, strongly agree, undecided, disagree, strongly disagree, then you would be using the Spearman's because that's the one you use for flow for ordinal variable. The type 1 and the type 2, which you would see now as we go into power, is a Wale. Go ahead with your question.
Thank you very much. Sorry to interrupt. I didn't really get what you just said now for the chi-square. You made a very sharp statement now concerning the exact and then the chi-square. You see, when we don't add a p-value and when we don't add a p-value for one of them, I didn't really get that.
Okay. Sorry, all right. So what I was saying is, let me show you a table, although I'll come back to this table. If you look at this table here, you would see there is a 42 here, there's a 10 here, there's a 23 here, there's a 4 here. We're looking at a pre and a post, differences between a pre and a post. Now, if we were not looking at a difference between a pre and a post, I will most likely be using a Fisher's exact P here. Why? Because I have 42, I have 10, I have 23, I have 4. 4 is less than 5. So if you look at the second table, 13, 39, 11, 16, and you have the percentages, for this second role, I would be using chi-square and p-value. But for this first role and this third role, I would use a Fisher's exact P. The reason is I have values less than 5 in them. But the reason why I'm using a McNeema test here, which is a type of a p-value, is because I'm doing a pre and a post. Anytime you're checking for differences in percentages for a pre and a post, you don't use chi-square, you use McNeema test. It's a type of a p-value and it doesn't have a chi-square. So these things are a bit tricky. I know sometimes people just jumble things up, but it's good to do things appropriately. So like I said, if you're checking for differences in percentages and all the numbers there are greater than 5, you'll be using a chi-square and a p-value because a chi-square is the test of significance used for checking for differences in percentages. So for this second role, if this was not a pre and a post scenario, chi-square and a p-value would have been appropriate for the second role. But for the first and the third role, Fisher's exact P would have been appropriate. Why? Because you have values less than 5. You have a 4 in the first one, you have a 1 in the second. But because we are looking at a pre and a post scenario, the McNeema test p-value is appropriate here. So I hope that is clear.
Very well. Thank you very much, sir.
All right. Thank you too for the question. So the hypothesis, there's something they call the hypothesis errors, which also play a role in the statistical power that I would be talking about. They have the type 1 error and the type 2 error. Now, I will explain them. In the type 1 error, you reject the null hypothesis when the null hypothesis is indeed true. For example, you're carrying out the research I mentioned. You want to look at the association between age and noise-induced hearing loss. If those that are older in age will have more noise-induced hearing loss than those that are younger in age. And you collected the data, you carried out the research, and you now realize that when you did the association, the p-value was greater than 0.05. Because associating differences in percentages, like I said, I'll probably be using the chi-square and the p. So the p is greater than 0.05. So what does that tell you? It tells you that there's no significant difference between age and noise-induced hearing loss. But as a researcher, you don't like that finding. Because sometimes, especially early career researchers, you feel that if your associations in your research does not show a significant p-value, you may likely not find journals that are willing to publish that paper, and that's not true. So you find out that the researcher does an association and the p-value is not significant, which means they are supposed to accept the null hypothesis that says there's no significant difference between age and noise-induced hearing loss, but they don't like that. So what do? They do what they call like p-hacking. They alter the data so that what was not significant before will now become significant. When you do that, you've committed a type 1 error, false positive, meaning that the null hypothesis was true. But because you don't like the fact that the null hypothesis is true, you want a significant association, you alter the data, and you have a significant association, but you've committed a type 1 error because you rejected the null hypothesis when the null hypothesis is true. The association says there's no significant difference, but you don't like that. You alter the data, it now becomes significant, and you say, whoa, there's a significant difference. But you did some manipulation on the data when you would have simply just accepted the null hypothesis. But you didn't want to accept it, so you committed a type 1 error. Now, the type 2 error, which is the false negative, this happens a lot, especially in the pharmaceutical industry. For example, as a researcher, you've been given money to see if a particular drug that is manufactured has a significant side effect. I mean, every drug has a side effect, we all know. But there are some side effects that are significant over the other. So you've been given money by a drug company to carry out a research to tell whether the drug they have manufactured has a significant side effect. And you carried out the research. And you found out that the drug has a significant side effect. But you didn't want to report that because you want to please your funders. That's why you see most of the time when you want to publish a paper, they will ask you, is there any conflict of interest? Did any drug company fund this research? Because the chances of committing a type 2 error is there. So you've done the association. The association is telling you that there's a significant side effect of this drug, probably in the heart, in the kidney, or wherever. And because you want to please the drug company, you tweak the data, adjust the data. So a type 2 error happens when the null hypothesis should be rejected, meaning you found a significant association. So because you found a significant side effect, you should have rejected the null hypothesis that says there's no significant side effect, but there was. But what did you do? You tweaked the data. And you failed to reject the null hypothesis, meaning that, so if you fail to reject the null hypothesis, what does that mean? There's a significance. You reported it, meaning you should have rejected the null hypothesis and said there was a significant difference, but instead, no, you failed to reject, meaning you accept the null hypothesis that there's no significant difference. So you've committed a type 2 error. You've committed a type 2 error when you accept a null hypothesis when you should have rejected it because there was a significant side effect. So the type 1 and type 2 error plays a role in the power. So let's progress now, since I've given us the foundation. Now, the statistical power, I have two scenarios. First is a scripture, Proverbs 24:10. That.
Hello, please, can I ask a question? Sorry.
Please go ahead.
Yes. Okay, so how do journal editors find out about these errors, the type 1 and the type 2 errors you just mentioned?
Well, it may not be easy for them to find out. That's why they ask your truthful contribution to that section. So they would ask you, that did you have any conflict of interest? And you have to state it. And one of the conflict of interest would be you're carrying out a research for a drug, and the drug company funded that research. So most of the time you may like to please them by trying as much as possible to make their product look good. So most of the publishers, they would accept whatever you put there in the conflict of interest. So there's no way, unless they want to carry out further investigations, into that, or they want to get an independent party to also carry out an independent research on that as well. And that could happen in a case where they probably want to put that drug in a country, and the prime minister or the president feels they are not satisfied with the research coming out from a particular research institution, and they want their own research institution to do the research. So these are scenarios where that could happen. So they just trust the information you give to them, but there's no way they would know. However, as a data person, like for me that I've had over 20 years working with data, a good number of times I can tell when a data is manipulated. Even for my students, I can actually tell when all these tests of significance were actually cooked and not calculated by the statistical software. I could tell, so sometimes they could have people like that in their team that could tell when a data is cooked, yeah, and that could be an outright rejection of that paper. So I hope I answered your question.
Yeah, sure. I understand now, because I've been seeing conflict of interest all the time, and
yes,
we usually say there is no conflict of, but per your explanation, I now get it. Thank you very much.
Thank you too. Thank you too. So we are now going into the cocoa of the topic, which is the statistical power. Now I have a scripture, Proverbs 24:10, which explains statistical power very well. Jeremiah please go ahead. Okay, so let's proceed. So okay.
Yeah, I want to find out whether journals actually publish the null hypothesis.
Yes, many times they do. But as an early career researcher, most times you would get scared that they would not. I mean, when you do a study that you accept your null hypothesis, it's a study. It's a scientific discovery. That's what you found. So okay, you should be proud to tell the world what you found. I mean, there's no need, trying to get statistical significance by all means when it's not there.
Okay.
That is when people commit type 1 error.
Because we are told in most instances that no journal will publish a null hypothesis.
No, I don't think so. That's not true, please. Yeah.
Okay, thank you.
The basis on publication is scientific rigor. That's the basis of publication. How scientific your research is, because they will look at the methodology, they will look at the data, they will look at the statistics, they will look at all those things. So once they're able to detect the scientific rigor in that work, irrespective of the finding, they will publish it. So you shouldn't be worried. Yes, Dr. Obere.
Okay, sir. With respect to the type 2 error in clinical trials, that is to get a particular drug, I think
yes,
the regulatory agency of a country and the ethics committee,
yes,
they are really involved in that, and they will almost get you at any point if you want to manipulate to achieve that type 2 error. They will almost get you, because even in that regulatory team, they have statisticians, biostatisticians, and very experienced people. So they will track you down, and in most cases, they will either stop or annul the trial.
Correct.
Thank you very much.
Thank you. Very,
so
very correct.
Difficult to bypass it.
Yes, very, 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 very. Like I mentioned earlier, if they have really good data people in their team, you know, it's very easy. Like I can tell when data are manipulated because of my experience working with different structures of data. You know, thank you for that contribution, Dr. Sally Sue.
Okay, thank you very much for this wonderful presentation. It's been mind-blowing. I would just want to ask, I'm curious, is there a kind of a statistical software to detect that, aside the clinical trials like the other participants shed light on now, like a researcher, a lecturer wants to test to be sure that the students have not committed the type 1 or type 2 error? Is there a way, or it comes with experience with time? Just
it comes with experience. It comes with experience. However, one of the easiest way you would be able to detect a type 1 error is data duplication. Because that is why we are treating statistical power. Statistical power helps you to avoid type 1 error. You know, very good you asked this question, which is launching me into what we're doing today. So you want to carry out a study. You don't just say, oh, I want to use 100. Oh, let me just use 150. Oh, let me just use 90. No way. In research is not allowed, because that number you are guesstimating may not have enough power to dictate if there are significant findings in that study. So you will end up, you know, making that study of no relevance when it should have been, if you had taken time to, you know, incorporate the evidence behind statistical power. So for example, now someone wants to do a study and they say, oh, I don't have time to collect enough data. Let me just use 50 participants. And you now use 50 participants and you now begin to do an association. You now find out that there's no significant difference for any of them. And you see that oftentimes, like from my experience, oftentimes when I run data analytics, especially when I start running tests of significance, and I start seeing no significant difference, no significant difference, no significant difference in almost all of the variables that are tested, one thing that could mean is that the power is small. Meaning the person probably didn't calculate a sample size. They guesstimated the sample size. That's why this part in Proverbs 24:10, it says, if you faint in the day of adversity, your strength is small. So it simply means if you're analyzing your data and you're not seeing a significant difference in almost every variable, it probably means the power of that data is small. You didn't pay a significance to the power of your data. So which is the question you asked. Oftentimes, how you could detect a type 1 error is you would see the fact that the data has been doubled, tripled, or something. So that, because they are now beginning to know that the moment you increase the number of that data, which is, you know, part of what you do when you're increasing the power, it has a way of increasing the chance of having a statistical significance. Obere.
Yes, thank you, sir. It depends upon the context of your research. If I'm doing a research with respect to rare disease, it will be very, difficult for me to get more patients. That is one. And also, one can just guess the sample size in a pilot study and do it. Then later you come and sit down and, use that with other literature and get the main sample size and carry out the main study. Thank you, sir.
Thank you too. Very well. Yes, there are some studies where you have a rare disease. However, you have to calculate the statistical power. That's the whole essence. So it's not really about the number. It's about the power in that study to detect a significant difference. You know, so yeah, so I know I have answered your question. So if you look at this table 3, this is a project we are currently carrying out in different states. So this is like a pre and a post intervention kind of training to know the participant knowledge on electronic medical records. So if you look at this, you will see that before the training, we had 52% filled the pretest. After the training, we had 27% filled. So you can see here now that the correct answer before the training was 80%. After the training was 85.2%. However, the McNeema test of p-value says there was no statistical difference. You can see an increase in knowledge, but it didn't show a significant difference. And one reason, if you check almost every of the variable, I think all of the variables, none of them showed a significant difference. Even when there was an increase in knowledge. Look at this one. Common EMR features, 25%, 40.7. This is an increase in knowledge, but the p-value was still greater than 0.05. What could be the reason? Power. The power for this study is small. There was no calculation of sample size here. There was no power calculation. It was based on the number of people that will fill. And that didn't work very well because we can see an increase in knowledge, but we cannot say there was a significant increase in knowledge after the training. We won't be able to say that because our p-value didn't show a significant difference. So one of the ways we can actually correct this, we will probably do that in the next training in Lagos, is to ensure that we have at least all of the participants for that training fill the pre and the post. So if we're able to get everybody feeling this, then we would have enough power to be able to show a significant difference if there is truly one in that association. Because looking at this, I can tell for sure that there's a significant difference between 25 and 40, but it didn't show because the power is small. So that's one of the benefits of ensuring that you incorporate power in your sampling. So the definition, statistical power, is a crucial concept in hypothesis testing and experimental design. Now you're clear on the hypothesis testing. So it is defined as the probability that a study will detect a real effect when one actually exists. So look at the example that I gave you, 25 and 40.7. That's a very good increase in knowledge, but it was not significant. It couldn't detect a real effect. It couldn't detect it because the power is small. So it's the likelihood of correctly rejecting a false null hypothesis. So the statistical power, look at the formula. Power is equal to 1 minus beta. The beta is the probability of making a type 2 error. What is the type 2 error? You're supposed to reject the null hypothesis, but you now accept the null hypothesis. So you're supposed to reject the null hypothesis. So it means that if we had enough power here, because if you look at this example I'm giving you, if we had enough power here, we will probably not be committing a type 2 error. If we have enough power here, our p-value may probably be significant. But because we don't have enough power, we are making a type 2 error, meaning we are rejecting. We are the probability of making a type 2 error, meaning that the type 2 error, you have a significance. Your study is showing a significant difference, but you are rejecting that significance. And you're accepting the null hypothesis that says there's no significant difference. So you're making a type 2 error. So in other words, in this example that I showed now, we should be having a significance, but we are not. We're not, because our power is small, so we are making a type 2 error. So the key concept in statistical power, you have the type 1 error, which I've mentioned already. The type 1 error should accept your null hypothesis. Your null hypothesis is true, but you reject it because you want to see a significant difference. Your type 2 error, there was a significant difference, you reject it because you don't want to see a significant difference. You now accept your null hypothesis when you should have rejected your null hypothesis and accepted your alternate hypothesis. So the power now is 1 minus b. Represent the probability of correctly rejecting the false null hypothesis. Simply mean if your alternate hypothesis is true, then you accept it. The alternate hypothesis means there's a significant difference. You accept it. All right? So in that way, you're rejecting a false null hypothesis, meaning you are not rejecting the alternate hypothesis and accepting your null hypothesis. So I will slow down here. And I know, like I said before I started, that this concept can be a little bit. So Emmanuel, your hand has been up. I don't know what
thank you.
Clarification you want. Yes.
Yeah, thank you very much. Actually, thank you for recognizing me. I just needed a clarification, especially with respect to power. Oftentimes, like I've had, like when you're doing a descriptive study, like a survey, that you don't necessarily need to be talking about power. That power is important when you are doing the comparative study, when you are trying to compare between one group or the other, trying to see the effect as you talk about. So what's your view from this perspective? That's what I'm asking. Like if
you would actually see the formulas. The formulas where you would have incorporation of power is those that are looking at associations.
Oh, okay.
So when you're calculating sample size that has to do with associations, comparison, you will see power incorporated in the sample size determination. Okay. But for descriptive, yes, you will not see power. You will see, I will show examples of that. Yeah.
All right. Thank you so much.
Thank you too. Yeah, Messi.
Yeah, hello, yeah. Please, how do you arrive by getting a numerical value for the beta for you to estimate the power of your sample?
These are constants. I would show you. The beta, they are constants. Okay. So like for example, if you want to do 80% or higher, you'll be aiming at 0.80, 0.84. So most of the times you'll be seeing 0.84, meaning that you are accepting a power of 80% or higher, which is ideal. It's like using 95% confidence interval to calculate the sample size for a descriptive. Meaning that whatever sample size you get, you are 95% confident that that is the sample size that will help you, have a result that is close to the population. Because you have to appreciate the fact that every study you do, you probably will not use the entire population. You will take a sample. So the sample size you're using, which will help you take a sample, whatever result you get from that sample, you will guesstimate it to be the same or representative if you had used the entire population. So that's why these percentages, 80% higher, gives you a level of confidence. The power on is that 80% or higher means if there is a significant, if there's a significance in that association, you will see it. It will come out. If it didn't come out, it means there's none. So the 95% confidence interval for the descriptive just tells you that whatever result, whatever percentage, whatever mean value you get would be close to the value if you had sampled the entire population.
Oh, okay. So a follow-up. So will I be wrong if I use this power, the calculation to detect if somebody falsified or got a type 1 or a type 2 error?
It will be the only way you can do that is to use the power to calculate the sample size yourself. So if you calculate the sample size yourself and whatever you calculated is higher than what the person used, then you can tell the person that your sample size has very low power. So meaning that you would not be able to detect any significance, even if it's there. So meaning the person is committing a type 2 error. The person is committing a type 2 error. A type 2 error, yes, simply means there could have been a significance, but because the number you're using is lower than the power, it didn't show. So it now seems as if we are accepting the null hypothesis.
Doc, I have a question to what you just said now.
Yeah.
You know, when you are constrained with either time or resources, how do you now balance the statistical power to be very high? You need it to be high, yet you have a limited time and probably your resources can't be able to attain to that sample size.
Well, the only thing you can do, that's why we have a section in our research called limitation. The only thing you can do is state your limitation. So anybody reading your limitation could tell probably whatever finding you got could have been better if you didn't have this limitation. That's all you can do. Yeah, that's all you can do. That's why we have the limitation section. That way people would be able to tell, probably this study may have been better than this, but these are the constraints the person has. So that may motivate someone else in another region to replicate that study and probably use a better sample or something, you know. Yeah. Okay, Mercy. Okay, I have attended to you. Otto Shem.
Yes,
so
thank you.
You've just done justice to it. Thank you.
Okay, all right, thank you.
So I just wanted to understand if there is a similarity between statistical power and then other methods that people can use to calculate sample size. For instance, some people can borrow methods that were used by other researchers from articles.
It's the same. It's the same thing. Oh. If you look at those formulas, if it's a formula like okay, I think when as we progress, you will see examples. If it's a formula that will calculate a sample size for checking for differences in two variables or something, there would be power incorporated in that formula. You would see the beta in it. It's there.
Okay.
Yes, it will be there.
Thank you.
Yes, you will see it. Yeah. The only one you may not see power, like someone mentioned, is when you just have a descriptive. All right. So let's progress because of our time. So these are some of the factors that will affect power. So the first one, the sample size, and I've mentioned the sample size aspect a lot, you know, telling us that when your sample size is too small, you may be committing a type 2 error. So meaning that the sample size is the sample size is too small to actually detect, you know, any substantial findings. And like someone just mentioned now, some of the practical constraint can be time, can be cost, and availability of participants. And this can often limit sample size, you know, which is why I said, peradventure you have issues like this, the best thing to do is to put it down in your limitation, so that when you publish the work, people could tell, okay, it probably could have been better, you know, but as a result of these challenges, that's why you have this number, you know, because oftentimes having too small a sample may be unethical, you know, because that study you are doing may have a significant finding, but because the sample is too small, the power is too small, it will now seem like we should accept the null hypothesis, you know? So that's the first thing that could affect, you know, the power, the sample size. The second one, the significance level. The default is 0.05. The default is 0.05. And for you to have a p-value that is 0.05 and lower, that sample has to have really good power. I showed you a very good example now in our own work. This is it. There's no p-value here that is less than 0.05. None. Everything is non-significant. Why? Because the power is small. So for you to be able to achieve 0.05 and less to show a statistical significant difference, your power must be really good. So that is why sometimes when researchers find out that their power is small, they increase the p-value. I've seen an instance where they use 0.5 instead of 0.05 because they know that the power of their study is small. They may not be able to, like, they will not get a statistical significant difference in any of the variable at all. None of the variable association will show a p-value 0.05 or less. So they now increase the significant level from 0.05 to 0.1 or 0.5, which is not a standard, but you could do that. All right. But the risk is there of committing a type 1 error because the association you didn't show a significant difference. The p-value was greater than 0.05, but because you have increased the p-value, it's now looking as if there is a significant difference when there is none. So you are committing a type 1 error. So that is why if you go through this route of increasing your p-value because you are using 0.05, you are saying that none of your association is showing a significant, and you want at least some of them to show a significant, you now increase your p-value to be 0.1. You have to have a strong justification for doing that. You have to have a strong justification for why you are increasing your p-value to 0.1, because the chances of causing a type 1 error is high. You will probably be saying this association showed a statistical significant difference when truly there was no statistical significant difference in that association. But because you have increased the significance level. So the importance of statistical power, research planning, like I had mentioned, you have to plan for your sample size. You don't just decide, oh, this is the number that I want to use. And like I mentioned earlier, when your power is low, your results may not be true. They may not be conclusive. And ethical consideration ensures that studies calculate their sample size appropriately and not guesstimate the number that they're going to use, because that will introduce bias and also publication bias as well. You know, because you would be producing false positives, making us accept a significant difference when a significant difference does not exist. You know? So, sample size determination, which the whole essence of the power we are doing is to ensure that we conduct a sample size determination for achieving our desired statistical power, for achieving the desired number that will be able to tell us if there's a significant difference in an association, if one exists. So, how do we calculate the sample size using the power? Now, this is the first scenario. Imagine a researcher wants to compare the effectiveness of a new drug against a placebo in reducing blood pressure. So they would be looking at the mean blood pressure before the person took the drug and after the person took the drug. So they want to carry out a study where they will have placebo and the drug, the new drug that they want to test. And for hypertensive patients, they will give them the new drug, and for the placebo, they will give them something else, maybe the standard drug, or they will give them something else, you know? So I want to carry out a study like this, and I want to determine my sample size. And I want that sample size to have enough power so that if there is a significant reduction in blood pressure as a result of the new drug, it will be there. The statistical significance will be obvious. So I need sufficient power to detect a meaningful difference between the two groups, so that if that drug is truly effective, it will show. Not that I'm going to guesstimate a number. Even when the drug is effective, I'm not seeing a significant p-value because I just choose any number that I like because of convenience. So I'm going to calculate the sample size using power. So the desired power that I want to use is 80%, which is 0.80. The significant level is 0.05, which is the standard, 5%. That's the standard. Now, the expected effect size, which is Cohen, we have small, we have medium, we have high. Medium is 0.5. I think I have a slide where I have the, oh, sorry, I missed the slide, where we have the effect size, which is also a factor. So there are other things, but the two primary ones that I mentioned here for effect sizes is the Cohen, which checks for differences in two means. Then the Pearson's, which checks the flow between two continuous variables. So for the Cohen, we have small, which is 0.2, medium, which is 0.5, and large, which is 0.8. So you decide if you want a small effect, or you want a medium effect, or you want a large effect. For Pearson's, it's the same way. 0.1 is a small effect, 0.3 is a medium, 0.5 is large. So you make the decision. But what you have to appreciate is the fact that the higher the effect you want to see, the more sample size. Oh. The more sample size, because the more number you have, the easier to detect a difference if it exists. So, but whether you're going to use medium or whether you're going to use large is at the researcher's discretion. So probably in this calculation, if you use medium effect and the number is too small for you, You can increase it to high effect and get more number. Okay, so here for this example, we are using medium effect and two-tail test. Now, p-values come out as one tail, come out as two tail. A simple definition I can give most of the time in public health, medical, I think sometimes in social research, we are interested in both ends. So meaning that we are interested in the effect, and we are also interested in those that didn't have the effect. For example, this experiment that you want to do now, which is checking if the new drug can bring down the blood pressure. You are not only interested in those that their blood pressure were reduced. You will also be interested in those that their blood pressure didn't reduce. That's why you're using the placebo. So in assumption, you think maybe the placebo will not have an effect in the blood pressure. So while you're looking at the new drug reducing the blood pressure, you're also looking at the other group where the blood pressure is not reduced. So that's why it's a two-tail. You're looking at both ends. But one-tail p-value is usually when you just focus on one side. Probably if you're interested in only the reduction of blood pressure, you're not interested in the other part, then you'll be looking at one tail. But the two-tail, most health research will look at both sides, both those that have the condition and those that don't have the condition. So these are the information that we're going to be using to calculate our sample size. So the step one, you determine the critical value. So our default 0.05, that's standard for p-value. Then the 1.96 is the standard normal distribution table. That is also a constant. 1.96 is a default. And we would demonstrate that. I will show you how the 1.96 came about. Just hold on. Then our power for 80%, 0.84, it's a constant, is a default. 0.84 is a default, is a constant. So now use the formula for the sample size. So this is the formula: 2 times the alpha divided by 2 plus the beta square divided by the d square. So the d square, which is the effect size, we're using 0.5. All right. So you add those things in the formula: 2 times the 1.96, which is a constant, 0.84, which is a constant, which represent the power, then the 0.52%, 0.5 square, which is also a constant, which talks about the Cohen effect we are tolerating. By the time you add all these things together, you're going to be having 62.72, approximately 63 participants. So using a power of 80%, 63 participants in each group has enough capacity to detect any change in blood pressure as a result of the new drug. So I don't know if I lost anyone in this calculation.
Yes, so.
Hello.
Yes, so where are you lost?
Hello, I'm just wondering if the intervention is not a new drug, but is, let's say, counseling services. Can you still use this formula?
Yes, yes, you can.
Okay, thank you.
You can, yes, you can use it in anything that you want to do, yes. So, but it will now depend, like I mentioned, it will now depend on the effect you want to see. So the sample size can change based on the alpha, based on the beta. So the level of effect you want to see, whether it's low effect, medium effect, or high effect, will determine the number that you're going to use, and that will adjust the sample size. And interestingly, you can also use, there are 2 softwares that I will show you that you can also use to calculate this if you don't want to do it manually. And those softwares are flexible because you can actually choose different values to get the sample size that you need. Yes, Dr. Mrs. Salisu.
Sorry, I'm here again. I was just
Sure.
going to ask about software. I like software a lot. We are in this year period now. Let's start announcing. But you have mentioned that. Having said that, I'm looking at we are looking at the two sample tests here, two-tailed test kind of. What if we have more than that? For example, some studies like can I go on?
Sorry, hold on. Let me mute. Okay. Okay. Please. Okay, go ahead, please.
Thank you.
Okay.
So I'm looking at from what I can get from this formula I've been trying to digest is like they are looking at if the drug will have effects. Okay, if the blood pressure drug we reduce and also increase blood pressure, that is the two ends, right? Am I right?
Yes.
All right. In a situation where you are looking at we have some studies that you have history, awareness, then you now have maybe you now have the test done. You now see the relationship between the pre-information and the information that you get after conducting the research. This time around, it's not going to be just 1, 2. You're going to have several responses for their history.
Okay, no, Mrs. Salisi, no, you are actually mixing explanatory variables and the dependent outcome. The dependent outcome will only have two sides. The dependent outcome for every study has two sides. Either they have that thing or they don't have it. Either they have knowledge.
Let me give you an example of what I'm saying. For example, somebody's coming for genetic tests now. We used to have like genetic counseling where we have a lot of history about the maybe genotype, for example. Then you now give them, they do not conduct the test. We will now see if there's a relationship between the pre-test history and the actual test results. Is that what you're saying? That's the kind of example I'm trying to.
No, that's not what I'm saying. What I'm saying is the outcome, meaning whatever study you are doing, what you want to detect from that study will have two sides most of the time.
Okay.
Yes. So like if you want to check, sorry. Okay. So like
you can meet everyone. I'll be listening.
Yeah. So if you want to check in your own case now, genotype, before you even started the study, you would have had in mind. Okay, let me just mute. You would have had in mind what you want to find out in that genotype. So I don't know what, but the fact I'm making is it's not the explanatory now, it's the dependent outcome. That's why you are doing that study. Most research, that dependent outcome would be either they have that thing you're interested in or they don't have that thing you're interested in. That's why you're doing that research, to see whether there are things that will influence whether they have the outcome you're interested in or they don't have the outcome that you are interested in. So that's where the two sides come in, yeah. So let me, Abdullahi, you can ask.
My question is probably maybe it may be different from the heading I'm seeing here as for two sample t-tests. Let's assume now I want to carry out I want to carry a survey among farmers, for instance, in different states. So how will I determine my total population?
Okay,
first?
good. I'm going to show you that. I'm going to show you that. We have other examples in front.
Okay.
Yes,
Okay.
I'll show you that. Yeah. God save.
Hi, can you hear me?
Yes.
Okay, I just wanted to ask, I know that N here is for minimum sample size.
Very good.
Assuming you calculated and your minimum sample size is, let's say 80, for example,
Yes.
and then you decide to go with a sample size of 250.
Yes.
Is there any problem with that?
No, your researcher will be very happy. The more the merrier. The more the merrier. So that's the minimum sample, meaning you can go above it, but you're not allowed to go below it.
Okay, so you can have as many
yes,
as you want.
Yes, but that minimum sample size calculate gives you a clue on the number you shouldn't go below. So the 63 is the minimum number, you know, that will be able to help you detect if there's any effect in the associations that you are testing. Yes. So you can actually go above. Yes, thank you.
Because I'm an undergraduate in my final year and it's just a prevalence study I wanted to do.
Study, okay. So I have a formula for prevalence study. I will show it. Is in front. Yes.
Okay, because someone was complaining that my sample size was too much. That why did I go more than double of the minimum?
It doesn't matter. The more the merrier. The more number you have, the more you're even able to detect if differences exist. Yes, it's okay. It's fine.
Thank you.
No worries. Who is remaining? Onyekachi.
Good afternoon, and thank you so much for the presentation. I think I have two questions. My first question is, when I was initially being taught about sample size, they made us to understand that it's because of either time or limitation in resources to get your entire population. Now, my question is, there are situations where I've got students who come to me and ask for me to calculate a sample size, but they are going through patient's record to extract information. And they want to get information from patients from, say, 2018 up till now. And they have access to the entire patient's record. Is it necessary to calculate sample size for those type of study? Then secondly, let's say, for example, another scenario was someone who came to calculate sample size again, but this had to deal with a dermatological condition. And then after calculating the sample size, because the population size is unknown, the number is so large, and he's like, we don't even see those number of patients in the facility. What's the way forward in those situations? Thank you.
So for the second one, remind me, I will mention it because I'm going to show you a formula with regards to that, because these formulas have what they call tolerable error. You can actually adjust, like here for this one, it is the Cohen-D effect. So you can increase or reduce the sample size based on the Cohen-D effect. But the other formulas I will show you, you can increase or reduce the sample size based on the tolerable error that you want to use, and also based on the prevalence as well. But I'm going to show you that as we progress. So the first question is, for academic purposes, even if you're going to use all the folders in the hospital, we want to see the minimum. It's called minimum sample. So meaning that's the minimum. The student is not allowed to go below. So for example, you calculate a minimum sample and your minimum sample is 200. And all the folders in the entire hospital is 120. What does that mean? It means you have to pick another hospital to make up that number. So It is the minimum sample. So if the student calculate the minimum sample and it's 200 and all the folders is 5,000, oh, wonderful. The more the merrier. So the minimum sample just gives you a clue on the number you're not allowed to go below. It doesn't mean that when you calculate it, it has to be that number, no. So it just gives, so if you calculate the sample size and it's 250 and you're using the entire record that is more than 1,000, fantastic. It just shows you that you have more number than you are not going below. Like for my PhD, when I calculated my minimum sample, it was, is it 1,000 and something or so? But my data itself, it's over 600,000 participants. It's over 600,000 participants because I was using data from 38 sub-Saharan African countries. So the data was over 2 million, but after cleaning up the data, I was able to have 500 and close to 600,000 that was eligible for the analysis. Yeah, so that calculation just gives you a clue on the number you shouldn't go below, not, you know, yeah. So yes, for academic purposes, yes, it is allowed to calculate sample size. At least it's a way of the student learning that you have to do this before you collect your sample. So for the next question, I would address it as we progress. So for the questions, hold your questions. Let's finish because our time is running. So this is one way of calculating. So you can verify what you've done using software. You don't have to calculate this manually. The two softwares here I'm using as an example, they are open source. The first one is G-Power. The second one is Arrow. So for the G-Power, here's the link. And these are pictures that I have here. So when you go to this link, you are going to see this. You download it. When you download it, it gives you a folder like this. When you click on that folder, you see 4 files inside. First of all, you should download the Microsoft Visual C++, because without this Microsoft Visual C++, you won't be able to run the G-Power because the G-Power uses the Microsoft Visual G++ to actually work. So you first of all install, not download, you've downloaded it already. You first of all install this second part, then you can now click this G-Power. That's how it's going to work. So when you click the G-Power, you are going to see an interface like this. So I'm going to exit this. So let us look at the G-Power itself. So this is it. All right. So you can use it to actually calculate sample size. So, but first, you have to decide the study you're doing. What are you testing? Are you testing differences in means? Meaning you're going to be using the t-test. You're going to be using the t-test. Or are you checking for differences in 3 or more means? That's the f-test. Are you checking for differences in percentages? That's the chi-square test and the z-test. So if you're checking for differences in percentages, you're going to be using the z-test or the chi-square. If it's differences in 2 means, the t-test. If it's differences in 3 or more means, the f-test. So you will decide the test. So the example we are using is t-test. So we're going to use this. Now it's coming here, the correlation, meaning that you are checking for if this is flowing. That is, so this is not what we are looking at. So we are actually looking at this difference between 2 independent means. That's the one we're interested in. You can also look at differences between 2 dependent means. That's the paired, like I mentioned. If, for example, you go into a community and you find out that probably the children are malnourished, you take their mean weights, you provide an intervention, 6 months later, you come back and take their mean weight again. In those scenarios, you are checking for differences in the mean weight before intervention and the difference in the mean weight after intervention. So you're going to be using the paired t-test. So that's where this one will come in, the 2 dependent means, which is the matched pairs. But in our own example, we're interested in 2 independent means. So the 2 independent means, and we're interested in sample size because there are many things here. Sensitivity is here. If you're doing a study where you are checking for specificity, sensitivity, then you will be using this one. But our own, we're interested in sample size, which is this one here, sample size. So we're going to choose that. So tail, we're interested in two tail. Effect size 0.5. Like you see, 0.2 is small, 0.5 is medium, 0.8 is large. So we're interested in 0.5. Then our alpha here is 0.05. That's the alpha we are using. Sorry, I think this is the one we are using. Is this first one? Sorry, is the first one. Compute required sample size, not the second one. Compute implied is not implied. Is the real deal. Sorry. So it's the first one. Compute required sample size. So it's two-tailed. Effect size medium 0.5. Alpha is 0.05. That's the default. Our power 0.84. That's 80% power. Then we are doing equal sample size, meaning control 20, intervention 20. But if you want to do 2:1, it depends on you. Then you can choose 2. If you want to do 3:1, you can choose 3. Meaning if you have 30 for the placebo or control, you can have 10 for the intervention. It depends on you. But in this example, we are using 1:1. Then once you put in all these parameters, you can now say calculate. So you can see the sample size here. For the first group is 71. For the second group is 71. So the 1.96 I was telling you, look at it here. So this is where it is gotten from. The alpha divided by 2, which is the T critical value, is 1.97, 1.96, 1.97. So this is normal distribution. This is normal distribution. All right. So this part in the normal distribution, this path here is the 1.96. All right. So that's where that alpha 1.96 is coming from. So it's a critical value. It's a constant, just like 0.84, just like 0.05, just like 0.5 of the effect size. So this is for G power. Then for the other one, which is Arrow Studio, I have the codes here, okay? So when you run it, you are going to find this, okay? You're going to have this. For Arrow is giving us 64, which is not too far from our own gave us 68. This one gave us 71. This one gave us 64. If you notice, they are all within the same. So they are different statistical software, so they may not give you the exact numbers, but it gives you a clue where your minimum sample size falls. So this is what the Arrow generates. So you see, from this chart, you can see that increase in the power increases your sample size. So as your power is increasing, your sample size is also increasing. So this is what you're having here. So you have 0.64. So in Arrow, the code is there. So when you get this PowerPoint, you can copy this and put it in your Arrow Studio. So this is it. So this is the code, all right? First of all, you have to install the package. For you to generate power, the sample, you have to install a package from your Arrow library, PW-Arrow. You can just type library in bracket PW-Arrow and it will run. Or you can come to tools here, go to install packages, and you can search for it, PW-Arrow. See it here. You can click on it, then you can install. So both ways, but you have to install this package first. You install the package, then you run it as library. Then you can now impute this. So you can use this my formula and modify it. Instead of 0.5, you can have 0.8 for large effect, you know. Instead of 0.05, you can have 0.01. Depends on what you want. Instead of power 0.80, you can increase your power, you know. So once you do this, all right. So for those of us that know how to use Arrow, so once you paste this, you highlight it and you run it. So you highlight it and you run it. Once you run, see it here. It's going to generate it here. Then if you want to copy the picture, you now have to zoom. So once you zoom, it is already here. So you can copy it and put in your work so that they know what your sample size is. Okay, so our time is running. So let's progress. Sorry. So I can show us the other sample size formulas. So for cross-sectional study, this is the formula that is usually used. It's from Kish. Z square PQ over E square. All right, so most cross-sectional studies are prevalence studies. You want to find out the prevalence of something. So everything in this formula is a constant. The Z is a constant, 1.96 square. P, you have to find the prevalence. So if I'm looking at doing a study on the prevalence of noise-induced hearing loss, I have to find a prevalence of noise-induced hearing loss in another study in my country. So if I'm doing the study in Nigeria, in Port Harcourt City, I have to see if there's a study that has been done in Port Harcourt City for the prevalence of noise-induced hearing loss. That's how I'm going to get my P. If I don't find a study in Port Harcourt, I have to find a study in any of the city in Nigeria. If there's no study on the prevalence of noise-induced hearing loss in Nigeria, I have to check in Africa. If there's no study in Africa, then I would have to check around the world. If there's no study on noise-induced hearing loss for me to get a prevalence, then I'll use a default of 50%. So using a default of 50% only happens when there is no study anywhere in the world for the prevalence of what you want to do. So you're not able to get your P. So you can use 50% for your P, and that will give you a sample size of around 400 and something. So this is the formula you will most likely use. The Q is 1 minus P. Then your tolerable error is 0.05. So you can adjust the sample size by, if you get a lower P, a prevalence that is very small, your sample size will be small. If you also adjust your tolerable error, your precision, your sample size will also be small. So it depends on you. Oftentimes, if you want to reduce your sample size, they would recommend that you find a prevalence for that study that is lower instead of adjusting your tolerable error, because 5% tolerable error it's the standard. You know, anything lower than that is not really good. However, if you increase your tolerable error from 5% to like 8% or 10%, that will increase your sample size and not reduce it. Because increasing your tolerable error means you would have to incorporate more sample size, because you've now increased your error, you need more sample size to adjust for that error. So using this as a formula, for example, this is an example of a study. Probably you are doing a study on utilization of, using the health center for delivery. So you have to find a similar study and you have to find a prevalence for that study. So for this study, 38% of participants delivered, in the health facility. So that is the prevalence for another study that you can use for your study. So you just impute that 38% in your P and also in your Q. So you will see that the Z is a constant, 1.96, but the P is the 0.38, while your Q is 1 minus your P. So 1 minus 0.38 will give you 0.62. Divide by the tolerable error, which is 0.05 squared. So by the time you do the calculation of this, you are going to have 362. So 362 is your minimum sample size, but you have to add a 10% non-response rate. All right. Now, what this does for you, it helps you, because if you go to the field with 362 exactly, you may come back with 360. And that's below your minimum sample, and that's not allowed. No number should be below 362. So that's why they say add a non-response. Those that may not, agree to fill your questionnaire, add 10%. So when you add the 10%, means you will be going to the field with 398. So if 8 people refuse to fill, you still have 390, which is above your minimum sample. Even if 10 people refuse to fill, you still have 388, which is still above your minimum sample. So that's why you're encouraged to add 10% before you take your questionnaires to the field. Because if you take exact 362, even if it's 2 people that didn't fill your questionnaire, it's below your minimum sample and you have to get that too. The second example is for comparative, like someone asked. When you're doing a study where you want to compare differences in percentages, this is the formula that you would use. So this is where the power comes in, which is what I was telling you. You're using a power of 80%, which is 0.84. So any formula that has to do with associations, you will have a power incorporated in it, unlike the previous one. So you have the 0.84. So you have the 1.96, which is a constant, 0.84, which is the power. You have to find a study that has a P1 and a P2, depending on what you're doing. So, for example, you are doing a study So peradventure, you are doing a study where you are looking at differences in percentages. Okay, you want to compare differences of 2 groups. Then you will probably be looking for a study for P1 and another for P2. Let me show you an example. Peradventure, you're doing a study where you are looking at serum selenium status of HIV-infected children. So you'll have 2 groups. The serum selenium status, for HIV and also for those without HIV. All right. So you have to look at have a study where they have a prevalence, for the selenium deficiency for HIV and selenium deficiency for those that don't have HIV. So that's what your study is all about. You want to see the selenium deficiency in HIV people and those that don't have HIV. So you have to look for a previous study that have these 2 prevalences. So your P1 would be the selenium, the prevalence of selenium deficiency in the HIV. Then your P2 would be the prevalence of selenium deficiency in the control, which is those that don't have HIV. So in this study, we have 24.3% for one group and 11.4% for another group. Then you're going to add that in your formula. So the alpha is 1.96 is a constant. The beta is 0.84 is a constant. So your P1 and P2 is what you're going to be looking for. The 24% and the 11%. So you're going to incorporate them here. And at the end, you will now say P1 minus P2, which is what we've done here. 24% is 0.243. 11.4% is 0.114. So this minus this. So when you calculate this, you're going to have 116. Then you're going to incorporate the 10%. That will give you 128. So it means your sample size will be 128 for each group. So because whatever sample you calculate using this formula will be for each group. All right. So that is it for this one. Okay, so we're going to move now. So this one, for this one is percentages. If you want to do a study where you're looking for prevalence, you're going to use this one. But if it is means, you're doing a study where you want to check for means, you are going to find a study that have a mean of what you're looking for. But in the formula is the standard deviation of the mean you are going to use to calculate the sample size. So this is a constant 1.96. Then you're going to put the standard deviation of the mean from a previous study square. Then your precision. So your tolerable error can be 0.05 or your precision can be 0.05, 0.02, 0.01. It's at your discretion. So is the adjustment of your precision. That's what determines how big or how small your sample size would be. But whatever sample size you get, that's what you should use. So that is the references for the different formulas and the studies that I have used. So, okay. So do we have any question? I think that is it for it. We still have some few minutes to take questions.
Felix?
Yeah.
I think we should move towards the question and answer session because like we only have 10-12 minutes of time left.
Yes.
I think we're done with the slide too, so it's about time.
Yes, we are done. Yes. So I'm glad I was taking question and answer in between. So I think we will not have so much now.
So there is this one that is in the chat box that I can read out.
Good.
Somebody is asking how to calculate sample size for comparative cross-sectional study. Example, compare cervical cancer rates among 2 regional areas.
Yeah, exactly. So this is the formula for that. This is the formula for that. Is this formula? Yes. So this is the formula you are going to use for that. Is this one. So if you're looking for differences in percentages, this formula is appropriate for you. Okay. So do we have any question again in the chat box that I missed before I take the live one? Or you can actually ask it live. So let me see. Hold on. Let me unmute. God save. You can ask your question. God save. Ask your question.
All right. Thank you so much for this impactful presentation. Can you hear me?
Yes, very well.
Okay, so I have 2 questions. Let me quickly ask. So assuming I'm working on a prevalence study, let's say the prevalence of hepatitis C within JAWS, and then my sample size is 180, for example, and then I decide to use maybe a multi-stage cluster sampling, and maybe I'm taking samples from the 3 local governments, assuming there are 3 local governments, and within those 3 local governments, I then choose to use 1 primary health care each from those 3.
Yeah.
Do I divide that 180 like within the 3 of them and do 60, 60, 60, or I have to divide it?
Do you want to take sample from the 3 clusters?
Yes.
Good. So if you want to take sample from the 3 clusters, then you will have to do a percent. So if you calculate your sample size, just a second, let me get something quickly and show you. Maybe it's better to show you than explaining it. Just a second. I hope I can find it quickly. Just hold on. Let me show you what you should do. Instead of talking about it, let me just show you. Let me see. Let me see.
Felix, there is this one question that just popped up. Shall I read to you?
Oh, yeah, please.
Okay. When we consider design effect, how is it implemented? How it is determined by rule of thumb 1.5 to 3 only, or calculated for specific sample size? It is the latest one. You can also see it in the chat box.
Okay. Okay, let me see. When we consider design effect, how is it implemented? How is it determined by the rule of thumb 1.5, 2.3 only, or calculated for specific sample sizes? I'm not clear on your question, but for the design effect, I showed you the numbers you can use for design effect for small, for medium, for large. using Cohen or using Pearson's correlation. So 1.2, I don't know how you got 1.2 and 2 point. You know, but you can ask your question, but just hold on. Let me show. Okay, I have seen the document I'm looking for. Sorry about that. So I'm going to share my screen and show you what I mean. Okay, very good. So hold on. Let me share my screen and show you what I'm trying to explain to you. Okay, so this is a sample size calculation. Oh, there. Okay, so yeah, so this is a sample size calculation. You can see my screen, right?
Yes.
Good. So I have, let me just go straight. I have calculated the sample size, which is 384. 384 is the sample size. Good. However, I'm recruiting that number from Bonds units, ICU, accident and emergency. So you have to have a table like this. So meaning the total population in each of the cohorts, you have to have it. Then you're going to use this formula where you will have the number in that cohort divided by the total population times the sample size. So that will now give you a number for each of the cohort. I don't know if you get that. At the end of the day, when you add all these numbers together, it will give you the total sample size you had calculated. Is that clear?
I'm trying to relate that with what I'm doing. So does that mean I'll have to know the total number of patients in that hospital?
Yes, you will need to know the population. If you want to recruit from each of the cohorts, you may not know the exact number, but you need a guesstimate number, because you can't just divide that number by 3 just like that abstractly. It doesn't work, because imagine one cohort has 20 patients and another cohort has 500 patients. Will it be fair to divide that number equally?
No.
It won't be fair, exactly. So
this number that I'm getting, so the total number of patients that come to that hospital, is it like, since I don't get, is it for this year? For I don't
No, the total number of patients they see. It depends on you, and it depends on the record they have. So whatever record they have, they should tell you what's the total number of patients they probably see in a month, or they probably see in a year.
So I can
So
use
it depends
a year
on
or
what,
month.
yes, you can use a year. Depends on what they're able to offer you. So once you have that number for the first cohort, you have that number for the second cohort, you have that number for the third cohort, you do a summation of it. All right. Then you have to do a formula where you will put the number for that first cohort for the year, divide by the total number for the 3 cohorts times the sample size that you've calculated. That will give you a number for that cohort. It will give you a number for the second cohort. So this will give you equal representation of the cohort based on the sample size for that facility. Or sorry, based on the population for that facility, so that you will not shortchange one facility over the number, because imagine a facility that has 200 people. You will pick your sample size faster than a facility that has 50 people. And now you're giving them equal numbers. So, but if you could reach me, I can share this template with you. I'm going to drop my number on the chat box. So if you need the template, you can, oh, sorry, I sent it to, where is everyone? Okay. I'm sending that number again. Sent it to a wrong group. Okay. So what's the difference between using Kish and Yemene? Kish, Yemene is population. I have an example of it. here. Yemene is when you know the population. This is an example of Yemene. This is an example of it. When you know the population you're working with, you can calculate the sample size based on the population. So the population for the unit is 8,182. Then the sample you want to collect, so you put that sample, you put the entire population, then you'll be able to get a sample size. But the other one is this one here, which I explained, where you will need a prevalence. That's the difference between the quiche, I'm looking for the chart. Okay. So the Yemene is when you know the population. That's the formula. Why the quiche is just prevalence you will use to calculate the sample size. Okay, let me take one more question in the chat before we go. Just a second. So I will take from Salisu. Salisu, you can ask. We have just 2 minutes.
Thank you, Dr. Felix. I'll reach out for others, but just the one I want to ask is that when you the last formula that you were supposed to get prevalence from two types of prevalence. What if you don't have prevalence of that study anywhere? I mean, this is the first time you are doing it. Like you suggested, I should use 50% for the one that we have to use just one prevalence from previous studies.
Yes.
Can we also use 50%, 50% for the P1 and P2 in case we don't get it from the literature?
No, you are not allowed to. The only way
if you don't have a previous study, what do we do?
Then you can calculate the prevalence study and divide it by 2. You can use the 50% for the prevalence study. It's for the prevalence formula itself. Then use 2 of that number. That's the only way. But
awesome.
Yeah, there's no adjustment for the other one.
Thank you. Thank you.
Yes, Ngozi.
Hi.
Yeah, good afternoon.
Yeah.
Can
you hear me?
Yes, I can hear you.
Just
I
just wanted to make a comment or question concerning sample size, because when you were talking, somebody talked about he calculated the sample size he wanted to use in his own study, and it was like more than double. And they were asking, why are you using more than double? So when I'm relating it to the one you calculated just now, that is 71, assuming your minimum is 71 from the one you showed now, and then maybe the person now decided to use 150. So I'm wondering, why is it not waste of resources if I use 71 or 75 and there will be no type 1 or type 2 error, and it will give us, there will be no error, it will give us what to expect, what we'll be confident that will show us the same thing to the entire population. Why should I be wasting resources?
It's not like well, I won't say it's a waste of resource. It's at your discretion as a researcher. If you're comfortable with 71, go ahead. But there are some researchers that have the opportunity to get more, and you won't stop them. Let's say you want to collect the data and you calculated 71, and when you found out that there were more people willing to be interviewed. Will you tell them, please stay, I don't want to interview you, I don't want to pass my minimum sample? You will not say that. You will take them in. And at the end of the day, you've crossed 71. But it's not of your making, but it's still allowed. So it's not a problem at all. Yeah, if you can afford to do that. Yeah.
Yes.
Okay. All right. Yes. So
I have to intervene here.
Up now. Yes.
Yes. I'm so sorry about that because we are past time. So I'd like to request everybody to turn on the video because there is this ritual at Authorate where we take pictures at the end for the memory and also to share on the social media. So if you are comfortable with it, please turn on your camera so that I can take a video. Turn on your camera so that I can take a picture, screenshot. Also, while we are doing that, we'd like to thank Felix from every one of us here at Authorate for this amazing webinar. I personally enjoyed it a lot, and I hope all of us did too. Thank you so much. We'll be sending you the recordings and the PowerPoint presentation of the webinar very shortly. Please stay tuned. Also, we have a lot of events coming up at Authorate. For that, we would like to request you to follow our social media, which I'm going to drop in the chat. We have community of more than 15,000 scholars, which you can join by joining our website and also our Google group. We have Twitter, Facebook, LinkedIn, Instagram, all of the places where we are actively sharing the opportunities and resources, blogs, news. So please stay connected there. You can also contribute the resources which you have found useful in the future, in the past, that you think will be useful for the scholarly community around the world. You can access the resources there. And you can also contribute the blogs and articles along with resources. The links are there. You can save it up for the future use also. Yeah. Okay. So thank you so much, Felix. I will take a picture now. I hope everybody is happy and everybody is smiling. Yes. So the first slide. Okay. Okay. Some fun poses. Like it's a weekend pose. Something happy. Yes. I'd like to see energy of the crowd, please. Okay. Thank you so much, everybody, for joining. We'd like to sign up now, and we'll be sharing the resources pretty soon. Stay connected with Authorate, and we'd love to see you in the further events too. Thank you so much. Thank you so much, Felix, for this amazing webinar. We enjoyed it a lot.
Thank you.
Thank you. Bye-bye.
Bye.